Swayam Prabha. Digital India. Educated India.
Okay, so let's go to the next. So this is this is the definition of a convex hull of a set. Another concept we need is that of a cone. A set S subset, which is in Rn, is said to be a cone if the following holds. So, if what I want to do is I want to take some alpha times S, or let me use a different notation, let me use lambda here. So, take lambda times S. What this is essentially is I am taking every vector x in the set and scaling it with lambda. But then I am going to scale it with a non-negative lambda. So, lambda times S is just the set S magnified or shrunk by lambda, by a factor lambda, right. So, every vector x has been just multiplied by a scalar lambda. Okay. So, my mistake here, I do not need this. But I am talking of lambdas that are non-negative. Okay. So, lambda S is this set which is where every vector has been multiplied by lambda. Now, the set is said to be a cone if lambda S belongs to S or is a subset of S. So, what does this mean? Belongs to S for all S, for all. So, what does this mean? So, you take any x, another way of saying this is for any x S and any lambda greater than equal to 0, the point lambda x also lies in S. Take any point x in S, take any lambda greater than 0, greater than equal to 0, then the point lambda x must lie in S. Okay. That's what then the set S is said to be a cone. So, what does a cone look like? So, a cone looks like a cone, right. So, but it does not have to look like a cone. So, for example, a set like this going all the way, right. So, if I take any vector x here and if I say suppose I scale this guy, this vector, it will scale reach here, maybe if I scale it by lambda. So, if this is my x, this will be my lambda x, or maybe it will get scaled down if my lambda is less than 1, this could be my lambda x. All such points are all in S. Okay. So, this sort of set is, this is a cone. Any other examples of cones? Yeah, line passing through the origin, that is a cone that does not look like a cone, right. So, this is a line passing through the origin, this is also a cone. Okay. Why? Because I can take any point x here, scale it, it lies on the line. Yes. So, now can a cone not pass through the origin? That is not possible, because by the definition I am allowed to take lambda equal to 0 here. If I can take lambda equal to 0, then it means that if I put lambda equal to 0, then here I am getting the left hand side as just 0. So, 0 must be in the set, right. So, a cone that's whose apex is lying somewhere other than the origin, this is not a cone for us, this sort of set. Okay. So, affine sets, for example, are not necessarily cones because they do not have to pass through the origin, but all subspaces are cones. Okay. So, but so you can, so subspaces are cones, these sort of sets are cones. You do not need to take the full subspace though, because you are not multiplying by negative scalars. So, I am not allowing for lambda negative here. So, I am not scaling in the opposite, in this direction, the opposite direction here, right. So, so what that means is a set that looks like this, say just a ray like this. This is also a cone, okay, although this is not clearly not a subspace. Okay. Okay. Now, is a cone convex? All these examples were convex. What about, is a cone always convex? Can you give me an example of a cone that is not convex? Yeah, I get what you are saying, but probably the word base is not quite the right word. See, so what he is saying is the base of a cone needn't be convex. What you are saying, I can roughly relate to what you are trying to say. But let me give you an example first in R2, and then we can come to these more exotic examples. So, what I have drawn here, these are axes, but this itself is a cone, right. So, this is my origin. I take any point, scale it by any scalar lambda greater than equal to 0, that gives me a point on the axis, right. So, this is a cone. I can not only that, I can take some other cross like this passing through the origin, these two. So, it's union of this line with this line, right, that is also a cone, right. So, this is also a cone. So, a cone need not be convex. What you are describing is a slightly more interesting sort of object. So, you can, it's not easy to do it in R2. In R2 there are limitations. So, I can try to explain to you how it would be. So, just think of some non-convex shape, say for example, some a star or something, just a cutout of a star on a page, shrink it down all the way down to the origin, and also grow it all the way till infinity. What you will be carving out in R3 will be this sort of the trace of this star sort of shape. That will not be a convex set though, because it will have this kind of boundary, right. Yeah. So, this is but that is a cone. Okay. So, it's so that sort of set is not necessarily a cone, is a case of a convex set that is not a cone. Okay. So, suppose if I gave you two cones C1, C2, if C1, C2 are cones, then what can you say about C1 intersection C2? What about the intersection of two cones? The intersection of two cones is a cone, but can also be a trivial cone. See, it can happen that the two cones are like say here's these two lines that they intersect on these two rays like this. They are individually cones, but their intersection is only the origin, right. So, the intersection can this is one of the you can have the problem that the intersection of two cones is this sort of trivial cone. Okay. Okay. Now, so we saw that the cone is not necessarily convex. So, this creates this problem of defining analogous things analogous to conic to convex combinations. So, if I give you points x1, x2 till xk that belong to say a set S. Okay, so, let S be in a set in Rn, and I give you points x1, x2, xk belonging to S. This and then this quantity summation alpha I x I, okay, let us call this y, summation alpha I x I running from 1 to k, where now the alphas there is no restriction on their sum, but they are just greater than equal to 0. So, all the alphas are just greater than equal to 0. This is what is called a conic combination. Okay. Now, if I take the set of all conic combinations, that means the a set like this summation alpha I x I running from 1 till k, alphas are greater than equal to 0, x1 till xk belong to S, and k is any natural number, right. So, this is the set of all conic combinations of points in S. This is what we call the conic hull of S, or the cone generated by S. Now, can you tell me how is this related to the smallest cone that contains S? How is this related to the smallest cone that contains S? It is, so it is not the intersection of all cones that contain S. It is not the intersection of all cones that contains S, and the reason for that is that this kind of conic hull is always a convex set. So, the conic hull is a convex cone. That is because of the way we have defined it. You will see it is very easy to see actually that if I take convex combinations of two points like this, 2 points in the conic hull, that convex combination also lies in the conic hull, right. So, a conic hull is not the smallest cone, but the smallest convex cone that contains it. So, just as an example, a very extreme example, suppose I take the set S as just having 2 points x1, x2, okay, in R2. So, my set is actually these 2 points, x1, x2. What is the smallest cone containing these 2 points? It is those 2 lines, okay, or 2 rays starting from the origin and one passing through x2, one passing through x1, right. So, the smallest cone containing these 2 would have been this. So, a point here would not be in the smallest cone containing x1, x2. But what about the conic hull? What is the conic hull of S1 of this x1, x2? So, when I take combinations alpha 1 x1 plus alpha 2 x2, where alpha 1 and alpha 2 are non-negative, what am I generating? Effectively, just think of your parallelepiped or whatever it is called, from high school geometry. So, you have x1, x2, alpha 1 x1 plus alpha 2 x2 would give you. So, this would be x1 plus x2, alpha 1 x1, maybe alpha 1 would be x1 would be here, alpha 2 x2 say here. You would get, this would be alpha 1 x1 plus alpha 2 x2, correct. And by doing this, when as I range over alpha 1, alpha 2 that are non-negative, I will basically span this entire region in, right. So, the conic hull is usually larger than the smallest cone, but it is the smallest convex cone that contains the set, that you can see, it is self evident here. Smallest convex cone containing containing x1, x1 and x2 is the V with the the interior in it. All right. So, now this gives me a chance to define a hyperplane. So, hyperplane is defined like this. So, you will take a vector A in Rn, take a scalar B in R. A hyperplane is simply all the x's that satisfy A transpose x equals B. So, hyperplane H is this sort of set, is x such that A transpose x equals B. You can also write it in the following way. You can also write this as, suppose you know that x0 is such that A transpose x0 is equal to B. That means, it is a point on the it's a point on the hyperplane, and this is the same as writing x such that A transpose x minus x0 equals B. Sorry, x minus x0 equals 0. Right. So, what this means is, take any 2 points x and x0 that lie on the hyperplane. Where does the vector A point? The vector A point is orthogonal to the segment x minus x0, right. So, in a hyperplane, when you write a hyperplane in this form as x such that A transpose x equals B, the vector A is the normal to the hyperplane. So, this is the normal. This is the normal to the hyperplane, right. So, because the hyperplane can be written in this form, x such that A transpose x minus x0 equals 0, then that also means that the hyperplane is actually nothing but x0 plus this A perp. What is A perp? A perp is that subspace which is perpendicular to A, right. So, it is the orthogonal complement of A. So, in the entire subspace which is perpendicular to A. So, this is the a hyperplane is different from what is called a half space. A half space is, again, let us suppose you have A in Rn, B in R, then a half space is x such that A transpose x less than equal. So, a half space is a hyperplane and one side of it. Okay, this is what we define. This sort of set is what's called a half space. So, is a half plane is a hyperplane a convex set? Yes. Right. Is a half space a convex set? Is a half space a convex set? Yes. So, it's this hyperplane and all of this, right. So, I can take any 2 points in it, and the segment joining those 2 points is always in the half space. Okay. So, a hyperplane and a half spaces, hyperplanes and half spaces, these are always convex. Now, remember I asked you, what if I took the wall here was a affine set, but the wall and the air in the room, all of that together, that was not an affine set. So, the wall is an example of that's actually a hyperplane. The wall and all the air on one side of it, that's a half space. Okay. So, a hyperplane in particular is always affine, but a half space is not affine. Okay. Final concept for today is that of a polyhedron. A polyhedron is the intersection of half spaces, intersection of finitely many half spaces. Okay. So, what that means is I need vectors like this, say a1 till am, all belonging to Rn, and I need b1 till bm, all scalars. Then you look at something like this, the x's such that they are common to the m half spaces that are created by these parameters, right. So, x such that ai transpose x is less than equal to bi for all I from 1 to m. This set P is a polyhedron. Okay. Another way to write this is to simply put all these ai transposes and make them rows of a matrix A, stack up the B's into a column vector B, into a column vector B1, stack up the Bi's into a column vector B, then your polyhedron P can simply be written as x such that Ax is less than equal to B. This for us is a polyhedron. So, is a polyhedron a convex set? Yes, it is the intersection of half spaces that are themselves convex. Okay. So, a polyhedron is always convex. A polyhedron is always convex. Is a polyhedron bounded? Is a polyhedron bounded? The answer is no, because a half space is a polyhedron, a hyperplane is a polyhedron, right. These are not bounded sets. a hyperplane is a polyhedron. Can you explain why a hyperplane is a polyhedron? Yeah, I can think of it as an intersection of two half spaces, one where you have so a hyperplane like this x such that A transpose x equals B is the intersection of x such that A transpose x less than equal to B with x such that A transpose x greater than equal to B, right. So it is an intersection of these two half spaces. So consequently, it is also a polyhedron. Hyperplane is a polyhedron. So every hyperplane is a polyhedron. A polyhedron need not be bounded. Polyhedron need not be bounded. Okay. Now, polyhedron should not be confused with another common term that is used, which is polygon. Okay. A polygon often stands for something like this. Some set like this is often what is referred to as a polygon. That is not what we mean by polyhedron. This sort of set is actually this sort of set, the one I have drawn right here, this is actually not even convex. Okay. So, a polyhedron for us is the intersection of half spaces. Okay. Polyhedron need not be bounded, but if it is bounded, so a bounded polyhedron is called a polytope. A bounded polyhedron is called a polytope. Okay. Now, what I want you to do as an exercise is to think of what a polytope would look like. So, it is an intersection of half spaces such that the overall intersection turns out to be bounded. Bounded means it can be put inside some ball of finite radius. So, but it is itself an intersection of finitely many half spaces. Okay. So, we can so think about it and we will discuss this next time.